Hi guys. So this will be the tutorial video for today's class, Friday the 24th, as well as Monday's class, the 27th, right? And what we want to do today is look at some equivalence relations and examples of some more obscure equivalence relations you may encounter. So we have this first question here. We define a relation P on the cross product of the set of integers by the ordered pairs AB and CD belong to P if AB is equal to CD. So just a reminder, what does this whole cross product mean? It means that if I had, let's say I want to take the cross product between two sets A and B, then this is equal to taking an ordered pair AB such that A comes from A and B comes from B, right? So this definition here just says that each member, this A, this B, this C, and D, each one of these are integer, right? So the definition of this relation is going to be A times B, the first times the second, is equal to C times D, the third times the fourth. And of course, to show that this is an equivalence relation, we need to do three things. We need to show it is reflexive, which means for all A, B belong to Z, then the ordered pair AB is of course related to itself. Then we need to show it is symmetric. So this one is for A and B in the set of integers, we have if AB and CD belong to P, then CD and AB belong to P, right? So this is symmetric, so you flip it. And the last one, transitive. Right? So if we have some AB, CD belongs to P, and some CD and maybe EF belongs to P, then AB, EF will belong to P, right? And of course, this is for A, B, C, and D are integers, and this one is for A, B, C, D, E, F are integers. Right. So let's go ahead and show each one of these. So proof. So first we will show reflexive. So to go through each one of these, you need to look at your definition of the relation. We're taking the first two elements and multiplying it by each other, right? So let's say we have an ordered pair AB. Then when we multiply those elements by each other, we have AB, which is of course itself AB. So what that means, if AB is equal to AB, you can sort of replace the CD in our definition here with AB, right? So this implies that AB is related to itself through P. Now, of course, this is for all AB belong to P, right? And that's it for reflexive. That one was pretty straightforward. Let's see, we have symmetric now, right? So for this one, suppose AB is related to CD, right? So by definition of the relation, this means that AB is equal to CD. And of course, if AB is equal to CD, another way of saying that is that CD is equal to AB. So this implies that CD is related to AB through P, right? And this is for A, B, C, and D belong to the interval, right? And the last one now, transitive. We suppose we have A, B, C, D in P and C, D, E, F in P. So again now, we just need to look at our definition of the relation. So first component times the second is equal to the third times the fourth, and first component times the second is equal to the third times the fourth. Right. So we can kind of consider this like equation one, and this one like equation two. And both of these equations are actually defined in terms of CD. So we could equate 1 and 2, and that gives us AB is equal to CD, which is equal to EF. Therefore, AB is equal to EF, which of course implies that the ordered pairs AV, EF belong to P. And that's it for transitivity. So if you see in each one of these, what we really do is we use the definition of the relation, which is the AB is equal to CD, and then we could use our preset rules that we know, like, you know, equating equations or flipping terms in the equal sign to draw the conclusions that we need to draw, right? So this belongs to P, hence the relation P is reflexive on Z. So we could actually write that in. So let's say hence P is reflexive on Z cross Z, and same thing here, right? So hence P is symmetric on Z cross Z. Right? And of course, this held for A, B, C, D, E, and F belong to the set of integers. Hence, P is transitive on Z cross Z. So what was the question saying? The question was saying to show that P is an equivalence relation on Z cross Z. So our conclusive line here is since P is reflexive, symmetric, and transitive on Z cross Z, P must be, by definition, equivalence relation on Z cross Z. Right? So I think when I'm done recording the video, I will export this as a PDF and I'll post it on my e-learning as well. So I think you guys have a question similar to this in the assignment. So hopefully this helps a little bit with that. right? So that's it for this example. So let's move on now. We want to look at a different example and call this one the congruence modulo relation, right? So when we say modulo here, we are talking about your modular arithmetic. So you all may have seen this in the back end of Unit 2 Pure Maths or maybe N1 Maths. But if not, when we talk about the congruence modular relation, this is how we define, right? So we put A is congruent to B mod N if N divides A minus. So this is our definition of this relation. So this sign here, this 3 equal signs, this means congruent, and this mod is short for modulo, which comes from modular arithmetic, right? So we won't go too much in depth behind the theory on modular arithmetic, but what we'll do is some examples on this relation. And what we'll actually show in the end is this relation here, this congruence relation is an equivalence relation, right? So it's all well and nice to have these symbols, but let's attach some numbers to it now so you all could see what it actually means to be congruent to modulo n, right? So we say that A is congruent to B mod n if n divides A minus B. So let's give an example. Example is 9 congruent to 5 mod 4. So by definition, so we take the mod n, so mod 4, and does this divide A minus B? Well, of course, 9 minus 5 is just 4. So does 4 divide 4? Well, the answer is yes, right? Of course, we could write 4 as 4 times 1. So this is an integer. So this is the whole A divides B if B is equal to AK, where K is an integer, right? So this is our divisibility definition, right? So we have 1 is an integer, so 4 divides 4. Let's look at another one. Maybe we have 23 is congruent to 18 mod 5. Of course, 5 divides 23 minus 18, which is 5, so that's true. We could have 27 is congruent to maybe 7 mod 4, right? So 4 divides 27 minus 7. 4 divides 20. Of course, this is true because we could write 20 as 4 times 5. Right? So this is the idea behind congruent modeling. So of course, this could actually also work this way. So let's say the A is smaller. So let's say we had 10 is congruent to 16 mod 3. Is this true? Does 3 divide 10 minus 16? Does 3 divide minus 6? And of course, the answer is true here as well, right? Because when we deal with this operation, we are actually defining it on the set of integers because divisibility is defined on the set of integers, right? So of course, for integers, it's just a side note. Of course, the set of integers is minus 3, minus 2, minus 1, 0, 1, 2, 3, etc., right? So Because we have positives and negatives, it works fine this way as well, right? And of course, we could even have negative numbers here. So let's say we had like minus 14 congruent to 2 mod 4, right? So 4 divides, this is a minus b, so minus 14 minus 2, 4 divides minus 16, right? So that's no problem at all. So this is the idea behind congruence modulo. So what the important takeaway here is that three lines equal sign there is just another equivalence relation, right? So we define the equivalence relation to be A is congruent to B mod n if n divides A minus B. So let's show that this is an equivalence relation. We're going to prove, so required to prove congruence mod n is an equivalence relation. Proof. All right, and as usual, the first thing we're going to show is reflexivity. We'll show it is reflexive. Right. So I'll just write it back here in red for you all to remember. So what is this relation? It says A is congruent to B mod n if n divides A minus B. So sort of just a sketch of reflexivity. If this is reflective, let's say we have A, then for A to be related through congruence mod n to itself, what we have is n divides A minus A. And that is, of course, true, right? Because A minus A is just 0. And n definitely divides 0. Any number divides 0, and you get 0, right? So could we write maybe something like n times 0, 0 is an integer, is equal to 0. And of course, 0 is just A minus A, right? So A minus A is divisible by n. I wrote it kind of back to front here, but this is what we're showing here. N divides A minus A. Therefore, n divides A minus A, which implies A is congruent to A mod n. Hence, congruence mod n is reflexive. And this, of course, is just the notation. Congruence, the equal signs, and what are we doing? We're doing mod n. All right, so let's show symmetry now. Symmetric. Right. So we suppose that A is congruent to B mod n. So what does this mean? By definition, it means n divides A minus B. And by definition of divisibility, it means that we could write A minus B as n times some integer, right? So of course, if 10 divides 100, then we could write 100 as 10 times some integer. That's what this is saying here. Right. So we have A minus B is equal to n times k, where k is an integer. Let's do a little rearrangement here. Let's actually multiply throughout by -1. Then we get B minus A is equal to minus nk. And of course, we could do a little associativity here. We could take minus k n. And of course, if k belongs to the set of integers, minus k also belongs to the set of integers. So what we have here is that b minus a gives us an integer times n. Therefore, n divides b minus a which implies B is congruent to A mod N. Hence, congruence modulo N is symmetric. All right, so the last thing now, transitivity. Transitivity. Right, so suppose A is congruent to B mod N and B is congruent to C mod N. What happens here? Right, then by definition, N divides A minus B, and we could write that as A minus B is N times some integer K. And what else? And of course, N divides, oops, not M. Right. N divides B minus C, which means we could write B minus C as N times some integer. We could call that L, right? So what could we do here? We have this one here. So this is equation 1. This is equation 2. So we could add equation 1 and 2. And what do we get? We get A minus B plus B minus C is equal to NK plus NL. A minus B plus B minus C, well, the minus B and plus B cancel off, and we're left with A minus C is equal to NK plus NL, which is N into K plus L. And of course, the set of integers is closed under addition, meaning that if we take any two integers and we add them together, we get an integer. So A minus C is N times an integer. Therefore, N divides A minus C, implies A is congruent to C mod N. Hence, congruence mod N is transitive. So what is our conclusion? Since congruence mod N is reflexive, symmetric, and transitive, congruence mod N is an equivalence relation. I didn't define the set that this is defined on, but we spoke higher up about divisibility being defined on the set of integers, right? So this is defined all on the set of integers. So A, B, and C are all integers, right? So maybe we could just put for all A belongs to the integers. Uh, EB belongs to integers and ABC belongs to integer, right? Yeah. And that shows that congruence mod N is an equivalence relation, right? So an important thing to note with this second example here is the idea of equivalence classes. So we briefly spoke about equivalence classes in Wednesday's class, right? So we know that the equivalence class, let's say we have a relation. So we have a set A, so a relation R defined on a set A. And let's say A is equal to A, B, C. Then the equivalence class of A was defined to be all the elements, let's say Y, such that A is related to Y. right? So in the context of this congruence modulo relation, what is the equivalence class? Well, let's take, for example, let's say we had mod 3, right? So we're looking at congruence to mod 3, n is 3. So just an example of mod 3. What does mod 3 look like? Let's say we have 5 that is congruent to 2 mod 3, right? And of course, we know this is true because 3 divides 5 minus 2. Next, so we're talking about mod 3 here, and we want to find the equivalence classes. So the notation you will see associated with this is actually Z3. And let's go over what this means. We know that A is congruent to B mod 3 if 3 divides A minus B, right? So to find the equivalence class, we need to see what elements B could be related to A. So there are actually 3 equivalence classes, right? Let's look at the equivalence class of 0. Let's just take the integer 0. What might this look like? You see, if we have 0 is congruent to B mod 3, what are the possible values for B? 3 divides 0 minus B. So B is just integer multiples of 3, right? Because we want to find all the values of B such that 3 divides minus B. So we can start. We can say minus 6, we have minus 3, we have 0, we have 3, we have 6, and so forth. So in this case, how could we get an element B that is related to A on the mod 3? Is all the integer multiples of 3. So let's look at 1. Okay. So if 1 is to be congruent to something, so now we're looking at 1, right? So 1 is congruent to B mod 3. So what do we need? 3 divides 1 minus B. But if you note something here, if 3 divides this, 1 minus B now must be a multiple of 3. So what are our B values? So let's see now. We know we want this to be a multiple of 3. So if 3 divides 3, then 1 minus B is 3, right? So 1 minus B is equal to 3. So minus B is equal to 3 minus 1. So B is equal to minus 2. Okay, let's see. What if we want this to be 6? Because 3 divides 6. So 1 minus B is equal to 6. Minus B is 5. So B is minus 5. And we could go the other way as well. So what if we wanted this to be minus 3, right? So 1 minus B is minus 3. Minus B is minus 4. So B must be 4. And that is how we are going to go down the line with this, right? Right. So we have our equivalence class of 1 now, and that is going to be all of these members here. And of course, we could extend infinitely on both sides, but basically what you get is, you know, we had minus 5, we had minus 2, we'll have 1, we'll have 4, and etc., right? And of course, the difference between each one of these, it goes up in 3, right? So minus 5 plus 3, minus 2 plus 3, 1 plus 3, so forth and so forth. And we could do the same thing to find the equivalence class of 2. So now, by definition, the equivalence class of 2, it will be 2 is congruent to B mod 3, which means 3 divides 2 minus B. So we need 2 minus B to be a multiple of 3. So what are the possible values for 2 minus B? Okay, well, when it is 0, We have 2 minus b is equal to 0. Minus b is equal to minus 2. So b is equal to 2. Of course, we could have it being equal to 3. Any multiple of 3. Minus b is 1. So b is minus 1. 2 minus b is 6. Minus b is 4. B is minus 4. And of course, we could go the other way. So 2 minus b is minus 3. So minus b minus 5. So b is 5. 2 minus b is minus 6. Minus b is minus 8. So b is 8. And so forth and so forth. Right, so the equivalence class of 2, we would have minus 4, minus 1, we'd have 2, 5, 8, and so forth and so forth, right? So when we reach the equivalence class of 3 now, what happens here? We want 3 minus, so 3 is going to divide 3 minus b, right? Because we want 3 congruent to b mod 3. So for this to be a multiple of 3, 3 minus b is equal to 3. Well, minus b is just 0, so b is 0. Or maybe we want it to be 9. 3 minus b is 9. Minus b, 6, so b is minus 6. So what we actually realize here is that if 3 minus b is a multiple of 3, then b is a multiple of 3. So we are actually back to our first case. So the values here will be minus 6, minus 3, 0, 3, 6, and so forth. But this is just equal to the equivalence class of 0. And that is the trick with modular arithmetic. The equivalence classes follow a cyclic nature. So the equivalence class of 4 is actually going to be equal to the equivalence class of 1. The equivalence class of 5 will be the equivalence class of 2. The equivalence class of 6 will be the equivalence class of 3, which is the equivalence class of 0. So there are only 3 distinct equivalence classes on the mod tree. And that is 0, 1, and 2. So these here are the equivalence classes for mod tree. So of course, these are 2 nice examples of equivalence relations. We have the congruence modulo n on the set of integers, and then we had this first one with the ordered pairs on the Cartesian product. So this first one here, you all will see something similar on your assignment. So hopefully this will help with that. And this second one here, this is very important for when we do tutorial sheets coming down to the end of the day, right? Nice. So of course, if there are any questions, you all could just email me or message on the WhatsApp group. But that would be it for today. Okay, bye.